Today we are going to look at how to develop the equation of a circle using Jock Macdonald's artwork, Fall. The learning goals for this lesson are to ensure that you can use appropriate mathematical vocabulary to describe a circle, that you can use Pythagorean Theorem to develop the equation of a circle, and that you know how to determine the equation of a circle given the location of its center and the length of its radius. So here is Jock Macdonald's artwork, Fall. At this point in the lesson, I would like for you to pause the video and take a look at the circles that you see in this image and compare and contrast those circles. Describe what is similar about the circles and what might be different about some of the circles. Now that you've taken a moment to do that, let's continue with the lesson. So looking again at this image, you may have started with the group of circles at the top part and described that they are different sizes. So using some mathematical terms, this would mean that these circles have different radius, different diameter, and that would result in them having a different circumference and a different area. In the bottom part of the image, there are two smaller red circles. Those seem to have the same size, but they are different locations in the artwork. So they are the same circle, but have been moved to different locations. If we look at the group of circles combined together in the bottom right, surrounded by the black box, that group of circles has the same center point, but the diameters or the radius are different. So the key idea here is that circles can be differentiated or described by their size using their radius or diameter. For the sake of the equation of the circle, we will focus on its radius. We can also differentiate a circle by the location of its center, where it is in the image. In order to move forward with developing the equation of a circle, we need to remember Pythagorean Theorem. So Pythagorean Theorem connects the sides of a right-angled triangle, and it states that the relationship between the lengths of the sides is as follows. A squared plus b squared is equal to c squared, where a and b are the variables used to describe the legs of the right-angled triangle, and c is used to describe the length of the hypotenuse. So if we take the two lengths of the legs and square them, then add them together, that value will be the same as if we took the length of the hypotenuse and squared it. And this is true for any right-angled triangle. We can use Pythagorean Theorem to find the length between 2 points by creating a right-angled triangle as pictured. So here we have the points 2, 3 and 5, 6. These coordinate points are used to describe the location of the point on a coordinate plane, where x is the horizontal axis, and the first point in the coordinate point is describing how far along the x-axis it is, and the second number in the coordinate pair is the value in the y direction, or the vertical axis. So here, the height of our triangle, or our a value, will be the difference between the two y coordinates. So for our points here, the first point has a y coordinate of 3, and the second has a y coordinate of 6. So this has increased by 3. So the length of the height is 3, which we could determine by taking 6 minus 3. The length of our base, or our b value, is the difference between the x coordinates. So again, looking at these points, our first point has an x value of 2, and our second point has an x coordinate of 5. So we've moved from 2 to 5 along the x-axis, again, a distance of 3. 5 minus 2 would give us the value of 3. So if we were going to try and find the length of this line segment between these 2 points, we could take 3 squared plus 3 squared, and that would give us 18. Now this is the squared value of this length, so to get the actual length of this line, we would need to take the square root of 18. In order to find the equation of our circles in the artwork, we need to add some context. So we can do that by placing the image on a coordinate plane. We have done that by uploading the artwork to an online graphing software called Desmos. Now we are able to find the location of points in this image. So let's take a look at one of these circles. In order to develop an equation for a circle, we need to keep it generalized. So we want to make sure that it will work no matter what circle we are using. So we're going to take this circle here and say that its center is at the point HK. And then we will take any point that is on the circle and we'll give that point the coordinates x, y. Using these points as seen in the image, we can create a right-angled triangle where the radius of our circle, so the line between the center point and our point on the circle, is now the hypotenuse of the triangle, or c. Using what we just reviewed from Pythagorean Theorem, we know that c squared is equal to a squared plus b squared, or in this case, c squared is equal to the difference between our two y values, y minus k all squared, plus the difference between our two x values, x minus h all squared. Since c is the same as the radius of our circle, we have now developed a generalized equation for the circle using the center hk and the radius as follows. X minus h all squared plus y minus k all squared is equal to r squared, where r is the length of the radius, hk is the center, and x, y are the coordinates of any point on the circle. Now looking at a specific example, in this circle, reading off of the grid, if we had zoomed out and had access to the x and y axes, the center of this circle has the coordinates negative 0.07, 2, and the red point that is on the circle is approximately 1, 3. So we can find the radius by substituting into the equation that we just developed. R squared is then therefore equal to 1 minus negative 0.07 all squared plus 3 minus 2 all squared. Substituting these values into the equation and simplifying, we end up with r squared is equal to 2.1449. For the equation of our circle, we need the value of r squared. We can therefore say that the equation is x plus 0.07 all squared plus y minus 2 all squared equals 2.1449. When we are giving the equation of a circle, we will always leave x and y in the equation. These are the values of any point on the circle. The other values are substituted in as the x and y value of the center and the radius squared. So going back to the start of the lesson, we said we can differentiate circles by their center and their size. So we have now come up with an equation that clearly states that this is the equation of the specific circle with a center at negative 0.07 and 2 and a radius of 2.1449. For more lessons and activities combining art and math, visit www.artofmathed.ca.